Hey guys, let's talk about networking here. Uh, Wireless networking is basically a radio signal, right? It encodes data into electromagnetic carrier waves that are radiated into the air using an antenna. So if you look over here in the radiation spectrum, this is where the radio waves lives, right? Take the 2.4 gigahertz Wi-Fi spectrum, for example. This orange line that I have showing here in this picture. As you can see, the lower the frequency, the lower is the channel that is transmitting, and the higher the channel, the higher the frequency. Another thing to see as a positive point here is that wireless broadcasts are not confined to the path of the wire because of its nature. So that's a very good thing. Depending on the type of transmitting antenna, you could have it either going all directions, which would be like it could basically cover a whole entire building, just one router, or you could have directional antennas that point in a specific direction. Um, Another thing they need to remember is that that is a certain limitation here, right? So because the signal travels in a straight line, right, regardless of you having an omnidirectional antenna or a directional antenna, um, eventually the signal is going to begin to drop, regardless of you having anything blocking, which brings us to another point here. Obstacles can block the transmission, and this is called attenuation. Wireless connections can not be shielded. That's another thing. Like you have the shielded twisted pair, shielding from EMI, electromagnetic waves cannot be uh, shielded from interference. So if you have like something, I mean, there are jammers out there that could block your radio signal. So that's one thing that you cannot account for, right? So the electromagnetic spectrum has a couple of elements here. One of them is wavelength. Wavelength refers to the distance between two consecutive waves. The shorter the wave, the faster they are. And when it comes to frequency, which is measured in hertz or cycles per second, you see that the higher the frequency, the shorter are the wavelengths. So that's why a 5.5 gigahertz uh, uh, frequency will be faster than a 2.4. However, the downside of it, or the upside of it, if you will, is that the lower frequency will be less prone to attenuation. So if you have like walls in the way, it's better for you to have a lower frequency, like a top 2.4 gigahertz than a 5 or higher, right? In that area. Um, Another thing to talk about is the Wi-Fi bands. As you were talking about the frequencies here. So in Wi-Fi we have the frequencies that we use is the 2.4 gigahertz, which is the industrial, scientific, and medical band, and is the most widely used in the Wi-Fi range. We have the 5 gigahertz, which is the ASM band. It is also common use, right? Just like the 2.4. The 5 gigahertz equipment tend to be more expensive. The range, again, shorter and again, more prone to attenuation, but it has 23 non-overlapping channels, while the 2.4 gigahertz has less. The 60 gigahertz wave band is used in some new devices. And you also have the VHF and the UHF frequencies, which are television stations uh, being targeted by Wi-Fi use, for Wi-Fi use. Uh, Wireless networking over time. This is a little brief history here. So the 802.11 was drafted in 1992, and in 1997 it was rectified. That's when Wi-Fi basically was made public, right, to the public. It was 2.4 gigahertz wavelength, I mean frequency, and it later became the 8.2, the 802.11a and the 802.11b. So the 802.11a was for enterprise purposes, and it actually operated on the 5 gigahertz wave band, while the 802.11b, which was the home version of it, was made for the 2.4 gigahertz band. Then we have the 802.11g and the 802.11n. Uh, and N actually had the 2.4 and the 5.0. And eventually we had, and as you can see here, it was the first time that it was the same standard for both enterprise and consumer. And then we now have the 802.11ac, which also operates on those two bands, but does a way better job than the N did. Transceiver is a connection point of the transmitter and receiver in the wireless node. Basically, what it does is it converts the electrical signals into waves, and it transmits the radio waves it receives into electrical signals. And so it does that conversion either to transmit or to receive. So if it is transmitting, right, it is converting the electrical signal into electromagnetic waves, and whenever, or radio waves, and if it is receiving, it's converting the radio waves into electrical signals. uh, it also uses to aid in the process the antennas that we mentioned. So the antennas could be omnidirectional, which affect all directions, or unidirectional, which is one direction. Transceivers also have the plex, that means when they transmit, they cannot receive. This type of approach is known as the carrier sense multiple access with collision avoidance. And basically, it operates like that. So if a device is transmitting, the other device is listening. So there is no like issues and collisions of the packets as they are in the air. So if you look over here, um, in the, oops, past the slide. Let me zoom in here. Oh, I don't have my zoom tool here. Anyways, oh, there you go. So if you look over here, this is more or less how it works. So station is waiting to transmit, right? So is it gonna ask if the channel is idle? So if the channel says that it's not idle, that is another device transmitting, it's gonna go back to the wait. And this is gonna be on a random period, right? So it's gonna check again if the channel is idle. That means it may be okay to transmit. So it's gonna wait for a random period, and if the channel is not busy, it will transmit. And if the channel becomes busy on the random period that is waiting, it's gonna go back to eating again. So this allows for the wireless networking, for the wireless communications not to have collisions, and make so that things are able to get to the destination with a reasonable amount of time. So let's talk a little bit about antennas here. You have the direction antenna and the omnidirection, as you can see here. Um, Let me zoom out a bit here. So for the omnidirection, there are two types. You have the isotropic, which is actually a concept. In theory, it should work, but we don't really have anything like that that works outside of theory. In truth, whenever you have an omnidirectional antenna, will not be an isotropic, it will be a dipole. For the directional antenna, it's also known as the Yagi. And I also put over here, it's a very interesting example of a Yagi antenna. Somebody picked up an antenna and actually used a Pringles box to make it directional. And it works pretty well. it can actually extend the signal of that directional antenna. Um, there are some more elements that I added to this slide here. As you can see, decibel isotropic, decibel dipole, and all that. These are elements that you guys, in your reading, as you guys get up to speed with IT, you might be curious to know what they are. So just put those. It's not needed for the exam, but it's some tidbits that might help you as you read stuff more advanced than this class. So managing bandwidth, a few things here uh, to keep in mind is you could strictly keep a wireless transmission to its own channel, and this is called narrow banding, transmission using one channel, but this leads to a limited data rate and is very susceptible to interference. Wireless technologies, Wi-Fi included, use different techniques to increase bandwidth to deal with interference. One is the spread spectrum, which breaks the transmission into a larger number of subchannels and nearby frequencies. To complete avoid interference, this means that you want to keep Wi-Fi hotspots in a few channels apart. So if we go back to the slide over here, that kind of shows the channels for the uh, 2.4 gigahertz here. Like for what it means about channels apart is that if you're on channel one, then you want to spread it, have the other channel use channel 11, not channel 6, right? This will avoid that two wireless channels are interfering with each other because of proximity, right? Now, another thing to keep in mind is if you do a wireless survey in your house, for example, right, and you start looking at how things are in the channels, you will see that everybody that lives around you is going to have their wireless device on different channels, but a lot of those are going to be very similar. And like for example, let's say you have like four neighbors and you have four neighbors on channel 6. That means that everybody in the vicinity has issues with bandwidth and interference on their wireless internet. So it might be a good thing for you to move your wireless router to a different channel, one that is open and nobody's using, right? Or very few people are using in your area. So this will definitely improve your connectivity. So let's go back here. Let's talk a little bit about MIMO. So MIMO, what it does, it the so it uses multiple antennas to provide simultaneous transmit and receive uh, on separate data streams on the same channel. So this solves the problem that we have with the what is it? The CS with the CSMA-CA, right? With the collision avoidance. MIMO came to help with that. I believe wireless N has MIMO. I know that the wireless AC actually uses the mu MIMO, which is a newer version of it, which allows more than one client with multiple antennas the ability to use the same access point with multiple antennas at the same time. So it's much, much more uh, um, valuable to the wireless network. Also uses something called beamforming, which each one of those devices actually have its own beam to the wireless transmitter, while the regular MIMO they all sharing the same beam. So it's the new MIMO. It's almost like we have the switch with the individual circuit between device and port. It's almost like that on a wireless level, the mu MIMO. That's why 802.11 AC it's way better than anything else we had before. Expanding on wireless local area networks. So due to the transceiver signal limitations, it is often hard to scale on WLANs. However, you can do the following to help with this expansion. You can use repeaters to extend the signal. The drawback with that is that the overall bandwidth is going to be reduced. You can use wireless access points with overlapping coverage using different channels. The problem with that is really management because since they all become individual networks, that means if you have to add a lot of wireless access points, you're going to have to always mess with the configuration of those individually. Uh, However, in an enterprise environment, you can have a thin client version of the WAPs of the access points, and have a wireless LAN controller manage those centrally. Now, what this will do is that you'll be able to send the configuration files to every access point from that wireless LAN controller, and they're all going to be on the same network. So this will be what you probably want to do on an enterprise level. Also, to further expand on it, there are cloud-based wireless LAN controllers that would allow you to manage not just local building, but several locations for a business. So if you have an office in Miami and an office in Fort Lauderdale, you'll be able to manage those with a wireless LAN controller over the internet. Um, you can also, another alternative, which is a new one, is the use of wireless mesh network. They're pretty reliable. Basically, what they do is they do a peer-to-peer between them and other IoT devices and the router. An example of those would be the Xfinity Pods or the Google Nest Wi-Fi, and they, from what I hear, they're doing really good. Local area technologies, a few terms here. You have the radio frequency, which is a generic term rather than a standard. It is used to describe radio frequency protocols. You also have the radio frequency ID, which RFID, which is radio frequency identification. This allows the identification and communication between nodes on the electromagnetic fields. There is Bluetooth, which is a standard, right? That is typically used for wireless private area networks applications. Several of the uses that you see, it's peripherals to computers or mobile devices like headphones, mouse, keyboards, stuff like that. Near field communication is a set of standards used on RFID. It's commonly found on mobile devices such as smartphones. A typical application of it will be something like Apple Pay. ANT Plus is a 2.4 gigahertz radio protocol similar to but separate than Bluetooth. This is the type of stuff that fitness trackers, medical devices, and watches are using. That is the Z-Wave. This is the stuff that is used to allow interoperability, monitoring, and remote control of home automation systems, right? And like lighting control, thermostats, like the Google Nest or other appliances that you could have in your home. And that is an open source standard to Z-Wave, because Z-Wave is actually maintained by Silicon Labs. So that is the ZigBee, which is the open standard, or the open source standard. Wi-Fi has two different operating modes. You have the ad hoc, which is basically a bunch of devices connected to each other. This is useful if you set up you go to set up a kiosk in an expo or the business or whatever, and you need a bunch of laptops connected to each other to demo some application or whatever. There is no centralized connection there. It's just a bunch of laptops connecting, networking locally to each other. This would be an application of ad hoc mode. Another application that you could see on an ad hoc node would be a bunch of it, I mean, like a pen. A pen could be essentially an ad hoc. You have your laptop, and then you have a mouse, a wireless mouse, and a wireless keyboard. I mean, a Bluetooth mouse and a Bluetooth keyboard connected to your computer. That's kind of like a ad hoc mode. Also, that is the infrastructure mode, which is typically what you see in a house or a business or anywhere else. Is when you have like the router, which is that central point, right? The central access point where all the devices connect to it, and this access point would either connect to a switch or would be its own switch, and would either also connect to a router or be its own router, which would then connect to the servers or internet. Like in your home, your wireless router is also a switch, and it connects to the internet, right? So that's what an infrastructure mode would imply, is when you have a centrally managed device, right, that mediates all the communication. While web, you know, while ad hoc mode, you don't have a centralized device. Everything is just peer-to-peer. Um, Wireless standards to memorize for the exam will be the 802.11g, the 802.11n, and the 802.11ac. I put all the information that you're gonna need. You're gonna need to know the speeds. You're gonna need to know the band that it uses, and so on and so forth. Now, a couple things to talk about here is that Wi-Fi interoperability depends on the weak it's link, right? So if you have 802.11g device, and the 802.11g device goes into a house that has the 802.11n, and everybody in the house has a 802.11n supported device. As soon as your visitor comes and connects to your Wi-Fi with the 802.11g device, everybody's speed, not just speed, but also encryption standard is going to have to drop. So if that device does not allow the encryption standard you have in our house, either he's not going to be able to connect, and if he does it, he's able to connect. It will be because either you have a lower encryption standard already set up out of the box, or you work with that person and you lowered while that visitor is in your house. However, the other thing, as I mentioned, the speed is also going to drop. So instead of you having the 600 megabits per second speed that you have with the N, you're now going to be getting the 54 megabits per second speed. Now, the 802.11ac does not serve for that. So if you go in the house, somebody that has that, what's going to happen is that that standard particularly uses the 2.4 gigahertz for all the weak stuff, right? And it does not compromise its AC standard, which lives 100% on the 5 gigahertz band. It doesn't. That's where it stays. So everything will be in your house connected there. So if you have visitors, they're all gonna be on the 2.4 gigahertz band without affecting you. However, still the encryption standards, same thing applies. If that person cannot handle encryption standards, then you're either gonna not be able to give them access, or they're not gonna be able to, or you're gonna have to lower what type of encryption you have in your house or business, right? New standards require MIMO to operate at their max, and devices don't operate, also don't operate to the 802.11 in strict terms. Some of these devices may have some proprietary variations to them. Last thing we're going to talk about here is wireless security. There are three types. We have the WEP, or wired equivalent privacy, which is super weak. It uses RC4 encryption cipher, and that's not why it makes it weak. What it makes it weak is that it uses this cyclic redundancy check, and when it does this, it only does so many cycles, and at some point you will show the share key or whatever way to get in the network in clear text. Uh, like so, if you're doing like a packet capture of this, you will eventually see the keys to the kingdom, so to speak. WPA got a little bit better because it introduced the KIP or temporal key integration protocol, which improved a little bit. You know, it made it 128-bit keys instead of the 32 bits that Web had. However, it's still crackable. I think really the addition that really mattered here was the fact that it added the 82.11x, which allowed it to work with radio servers or EAP. But things didn't really get good for security until the WPA2 came into place with the AES encryption standard, right? So you really improved everything. So 802, the WPA2 is the best protocol to have when it comes to wireless security because of the 128-bit encryption that it has. So there are some more elements here that I threw for you guys to read about it, but the main thing is the WPA2 is the strongest. WPA is not. It's just a little bit stronger than WEP, but they both are fairly easy to hack. Another thing to that I put it here is that WPA has three options. You have the personal, which would be a pre-share key. You have the enterprise, which operates on the 802.1x, which radius based. So this allows authentication with Active Directory servers and stuff like that. You could have two-factor authentication on a radio server as well. So that's an extra layer of security there. Another element here is the WPS or Wi-Fi protected setup. It was made to make it easy for people to, whenever they have a guest in their home, just click a button on the router and the person gets access to their wireless network. It's not very secure. It's a very, very insecure option to have enabled. I don't recommend anybody having it, but it's something that is also an option on WPA. So this concludes our slideshows for chapter 14, and I'll see you next time.